We have been looking at partial differential equations and methods of solving these equations numerically, in which we saw one particular case of an elliptic partial differential equation of the form del squared u by del x squared plus del squared u by del y squared equal to 0. And we solve these equations by writing down the second derivatives as difference equations, and we wrote del squared u by del x squared as u at x plus delta x minus 2 ux plus u at x minus delta x divided by delta x squared, and similarly for delta y square. And we found that these equations we can solve iteratively by writing it in the following form. That is, if you substitute these equations for the second derivatives in the difference form in these equations, the equation which we have, if you substitute these terms into that, and this in the case where delta x and delta y are the same. So when delta x equal to delta y, we can write these equations as so that's what we saw in the last lecture, that I can substitute this difference equation into this and then write this equation, this particular equation in this form. That is, the u at x y is written as ux plus delta x comma y, ux y plus delta y, ux minus delta x y, and ux y minus delta y whole divided by 4. So that is what we wrote, and we solve this iteratively. That is, to start with, we divide the space into a grid, right. So we divide this into a square grid, and then we had the values specified at each of these grid points to begin with, okay. And then at the next step we would evaluate the values at each grid point by using this procedure, this equation, okay. And we will continue this procedure till we have the left two sides are the same. That is, when ux y obtained in the next iteration loop is the same as what was in the previous step. So that was the way of solving the elliptic equations which we did in the last class. So now we look at slightly different form, okay, that which in which now we look at equations which are time dependent. So this particular equation we solved in the context of the distribution of temperature. As we said, that if you have a slab in which a conducting slab, and which is kept at whose boundaries are kept at different temperatures. For example, this is kept at, let us say, 100 degrees, and this is 0 and 50 and 75. And the slab is insulated from the top and the bottom, so that the whole heat flow is only inside the plane. And then we wanted to know what the temperature distribution would be, okay. And that we saw that leads to an equation of this form where u is the temperature. Okay. Now the same problem, if you want to look at the case where it's time dependent, okay, that's we want to know how does so now this is a steady state equation. So now we want to know how, starting from a given initial condition, that is, this is kept at 100, 75, 50 and 0, and everywhere else also it's 0 to begin with, and we want to know how does it go into the steady state. And in that kind of cases we will have to solve a time dependent equation. So in this course, okay, we will only look at one dimensional time dependent equations, that is one space dimension and then one time dimension, okay. So that we will look at only those particular cases, okay. So that is equations of the form, we will be looking at equations of the form del u, where u is again temperature, is equal to some coefficient times, so t, this little t is the time here, some coefficient times del squared u by del x squared, okay. So we look at equations of this form. So here is one example where this arises. in the case of a heat conduction through a thin rod. Okay, so I assume that this to be a very thin rod. Okay, so that across the cross section we can assume the temperature to be uniform, and let us say it is insulated all over its length. So what is exposed is only the two boundaries, and the two boundaries are kept at two different temperatures, and we want to know what will be the temperature distribution along the length of this rod as a function of time. Okay, so that problem would lead to an equation of the form which I just wrote. So we are not looking at steady state here, we are looking at this long thin rod. Okay, thin, we assume it to be thin so that we can we take it as thin so that we can assume that in the cross section, across the cross section, the temperature is uniform and it is insulated all along its length. Okay, so the heat enters here and goes out here. So you take any element where the heat comes in here at is Qx, and what heat goes out here is Q at x plus delta x. So that will be the heat flux, right, into the cross sectional area, which is, let us take it as A. So the heat flux, let us take it as Q here, and then Q of x, and then what goes out will be Q at x plus delta x, as we saw earlier. So now we know that the Q is the gradient of temperature, that is del U by del x in this particular case. Right. So these equations would lead to something like this. So we consider the element delta dx, right, and then the heat enters at x and it goes out at x plus dx. Now the amount of heat that flows into this thing is Qx, as the Qx is Ka into del U by del x. We know that, that's what we, this is a Fourier's law. So what the heat enters is a Qx, okay, at this point here. Okay. So that is K times A into the gradient in the temperature. U is the temperature here, so gradient in the temperature. A is the area and K is the heat conduction, the coefficient. So that is what we have, and then we can write and we know that this heat which goes out here is Qx plus delta x. Okay, so the net change in the what comes in and goes out would be equal to del. So what? Okay, so let me write this in this form. So you have this rod. So we are considering this particular section. So what comes in here is at Qx, and what goes out here is Qx plus dx for this thickness, and so the change would be, so Qx plus dx can be written as Q of x, right, plus del Q by del x into dx. So what goes out of what is retained here, the heat which is retained in this section is Qx plus dx minus Qx, which is del Q by del x, del x to del Q by dx. So Qx plus dx minus Q of x is del Q by del x into dx. Okay, that is what we have. Okay, now this Q itself we know is minus K times A times del U by del x. Okay, so substitute that here. So the heat retained here per unit length per unit area. Okay, so the heat which is retained in this area per unit length per unit cross sectional area would be given by the heat retained would be per unit length per unit area would be del Q by del x, right. So that will be the heat which is retained here. Okay, per unit area per unit length would be, so 1 over into 1 over A. Okay, that will give us K times del squared U by del x square. Okay, now that heat which is retained causes a change in temperature there. Okay, so that rates the equation that del squared U by del x square into K is del U by del T. So that is one case where you get this equation, that is some heat comes, take a long thin rod, okay, insulated on the sides. Okay, so heat comes in here, goes out there, and the cross section we assume the temperature to be uniform, right, and then the heat comes in here. If we take a unit take an element of length dx, what comes in here is Qx, what goes out is Qx plus delta x. So retained is del Q by del x into dx. So the heat which is retained per unit area per unit area cross section per unit length would be, again, will be 1 over A del Q by del x. okay, but we know Q is Ka into del U by del X. So we get the heat retained is actually del square U by del X square, and that retained heat is actually used for increasing the temperature there. So the rate of change of temperature should be proportional to the rate of retaining of the heat. Okay, so that gives this equation del Q by del X. Right? So that's one example. Okay, so we saw the steady state case in the Laplace's equation. Now we are looking at this case where the temperature changes as a function of time. Okay, so now to conclude, what we want to look at is an equation of this form, okay, and we want to know how we can solve this numerically. So again, we could write del squared U by del X squared as U at x plus delta x minus 2 ux plus u x minus delta x divided by delta x squared, and we could write del u by del t as u x t plus delta t, right. Okay, now this is all okay. So now I can write like this, and then minus u x comma t divided by delta t. So that's a forward difference method of writing the derivatives del u by del t. Okay, now the question is, so now we can do this. Okay, so we can, there is a choice here, that is when you substitute this into this equation. Okay, whether, since this is only a derivative with respect to time, okay, I can write this as u x plus x t plus delta t minus u x at t divided by delta t at the same position x. Now the right hand side is only a derivative with respect to space variable x. Then the question is whether we should take this derivative at time t or time t plus delta t. So there is a choice there. So what I am saying is that you can actually evaluate this derivative at either t or at t plus delta t. So that leads to two different methods. Okay, if I evaluate this at t, and I would call that as an explicit method, and if I evaluate this derivative at time t plus delta t, I call that an implicit method. So these are two methods which we should be looking at today. Okay, so today our aim is to solve this equation, okay, this particular equation using two different methods, that is substituting for these derivatives the difference equations, but taking the space derivative in one method at time t, okay, and that is called the explicit method, and another method in which we would take this derivative at time t plus delta t, and that would be called the implicit method. Okay, we will look at these two methods, these two equations. So let me summarize this again. So we want to look at equation of this form, which arises in the case of a thermal transport in a long thin rod, right, and the time dependent equation for that, and we want to solve this, and we will discuss two different methods, and one is the implicit method in which the second derivative here u is evaluated at time t plus delta t, and there is another explicit method in which this is evaluated at time t. So here is the explicit method. Okay, so it is very similar to the one which we use for the steady state case. Okay, so we replace the second derivative here, the del squared u by del x squared, by this difference equation. So now the notation we use is the following, that we discretize space, and with the space positions are known L. Okay, so u of x we call as u L, okay, and u x at time t. So u x at time t we would now denote by u L t. So u x plus delta x at time t will be written as u L plus 1, because it is equally spaced points we are going to take. We are going to take equally spaced points in the spatial variable. So it is u L plus 1 time t. Similarly, t plus delta t will be t plus 1 here. Right. So here we are taking all second derivatives at time t. Okay, so that will be u t L plus 1 minus 2 u L t plus u L minus 1 t. divided by delta x squared. And now there is the time derivative del u by del t as u L t plus 1 minus u L t by delta t. So now these two equations, okay, substituting into our time dependent partial differential equation, we can write that as this one, okay, that is u. Okay, now what we did was substitute these two into this equation. Okay, so we are going to write it in time t. So we are doing explicit method. So all this is evaluated at time t. So what do we get if you do that? So we are going to get u L at t plus 1 minus u L at t divided by delta t is equal to u L plus 1 at t minus 2 u L t plus u L minus 1 t divided by delta x squared, and there is a k, a coefficient here which is k. So that is the equation we have. So we can rewrite this in terms of, so what we want to find out is what is the temperature at t plus 1, at time t plus 1, right. So we can write u L at t plus 1 is equal to k times delta t by delta x squared into u L plus 1 t plus 1 minus 2 minus 2 u L t plus u L minus 1 t, okay, plus, so now we have, so now plus u L at t. So that's an equation which we will be writing. So this is easy to solve because at given time t, that is at given time t equal to 0, for example, or at any starting time, we have been given the position, the temperature at all the points. So we have this particular rod, long thin rod, okay. So we have been given the conditions at the boundary, okay, and then we write, so we discretize this into equal intervals in space, okay, with interval delta x, right, and at time t equal to 0 we have given the position, the temperature at all the points. We know what the temperature at all the points at time t equal to 0 is, right. And then at time t plus 1, that is t plus delta t, what is the temperature is given by this equation. So the right hand side is completely at time in terms of temperature at t, and the left hand side gives us the temperature at t plus 1. So using this equation we can easily solve this. So now this term is called the parameter lambda. So that is called lambda. This equation, this particular parameter is called lambda. K times delta t by delta x whole square. So now note that one problem with this equation is that it is second order in delta x, okay, in space variable, and it's first order in time. So because of this particular reason, it's not equally, its sensitivity is not the same in terms of the spatial discretization and time discretization, okay, that's reflected in this particular parameter. So that is when we change delta x, what's the effect which it has on this equation is not the same as when we change delta t, the time discretization. So we have discretized both space and time here, but the effect of the discretization on the stability of these equations are not the same for time and space, okay, and that's because it's first order in time and second order in space derivative. So this simple equation can be used to solve the heat equation, but only problem is that this particular equation is found to be extremely sensitive to the value of lambda which we use. That is, this, if you use a very large value of lambda, this is unstable. We have to use small value of lambda, that is we have to use lambda typically less than or equal to 0.5, okay. So which is less than or equal to half to get a good results on this equation. Okay, that's the biggest problem with this with this equation. Otherwise, it is extremely simple that we know at all time, at the starting time, in the initial time, if you know the temperature at all points on this rod, okay, we can use this equation to get the temperature at the all later times, okay, using this once we have fixed this quantity lambda. So that's what's written summarized here. So we have this special derivative written as the discrete equation, and there's a time derivative written again using the forward difference equation, and we substitute that into the heat equation, and we obtain an equation, a simple equation of this form, okay, where lambda given by k times delta T by delta x squared. So now we can use given a time the temperature at time t minus 1, we can compute the temperature at time t using that equation. Okay. So now, as I said, the problem with this method is that this method is convergent, that is stable only when delta t is less than or equal to delta t square by 2k, or lambda has to be less than or equal to half, lambda being k times delta T by delta x square has to be less than or equal to half, and that is what we see. So now that's a problem with this explicit method. Okay. So if you want to the implication of this is following, that if you actually change the grid size delta x in spatial grid, we also have to change the delta t correspondingly. Okay. So it's time, if you want to keep the lambda a constant, okay, that is, so that if we choose a lambda for which this equation is stable and gives a stable solution, and you want a little more, let us say, spatial resolution. Okay. So we want to know, so we choose a particular delta x and we solved this problem using this, solve this equation using this particular explicit method, and then we want to increase the resolution in space. We wanted the temperature a little more close each other, that means we want to reduce delta x. So what happens is, if you change delta x here, to keep the lambda the same, we also have to change delta t. Okay. So you can see that if I actually half the delta x, okay, so to get the same stability and to see that the equation is stable, I have to go 1/4 in delta t, right, because this is delta x square or this is delta t. So if I want to increase the spatial resolution by going to half the space distance, that is the discretization, if I half my discretization in space, okay, then I have to go 1/4 in time. Okay. So my computational expenditure will go up by 8 times. Okay. Right. So to solve that for a given time t, we have discretized both time in intervals of delta t and space in terms of delta x. But we wanted a higher, if you want to go to higher accuracy in the spatial variable, and if you half the delta x to keep the same lambda so that the equation is stable, we have to go 1/4 in delta t. So that means we will increase our computational expenditure by 8 times. So this is one of the drawbacks of this particular explicit method. Okay, we will see this method implemented in a program before we go and see a little more accurate method, which are the implicit methods. So we look at this program which uses the explicit method for solving the heat equation. Okay, so we are using a lambda which is equal to 0.5, and what we do is we discretize the space into 5 points, and you use the explicit equation, which is saying that s at j, it's actually saying that s at j plus 1 plus s at j minus 1 and 2sj, right, minus 2sj multiplied by lambda added to sj is the next one, which I store as d of j here. Okay, so d is time t plus 1 and s is time t. That's what we are going to use. So before we start that, we need to see that we need some boundary condition, that is, we have these equations, okay, and I am using in the program the variables at time t as s and the variable at time t plus 1 as d, the temperature, and then we need to implement this equation at every point on this discretized space, space. The problem is, again, as we saw in the Laplace's equation, that we can't use this equations at this two initial point, two endpoints. Right? Here we don't know what L minus 1 is, and here we don't know what L plus 1 is. Okay. So either we have to use some boundary conditions. The boundary condition could be that at the two endpoints the temperature is specified. So we could say that this is equal to 100, and u is 100 here and u is 0 here, or we could use the derivatives at the two boundaries. If you fix the derivatives at the two boundaries and get the temperature corresponding to two fictitious points at that side, so that the derivative can be fixed, and then we would have to solve for all the points including the boundary points. So in the case where the boundary condition is specified in terms of the variable at the two boundaries, that's what the program is for. Okay, we have to solve only for the interior points. Okay, so this two boundaries, the value of u or the temperature is fixed for all time. For all time it is fixed as 100 and 0. Okay, and we solve for all interior points using a lambda equal to 0.5. So that's what we do. Okay, so we have time going from 1 to 50, okay, and we solve this for every time step. So start with everywhere else it's put as 0. Okay, so one end is kept at 100 and every other point is kept at 0 to begin with. Okay, and the last point is always maintained at 0. Okay, so that's the two boundary conditions which we have. Okay, so now we solve this using this. So this is a time t plus 1 and this is a time t. So time t plus 1, the temperature is equal to time t plus lambda times this particular the second derivative of the function. And then after that its calculation is over, I transfer the time t plus 1 to time t and then goes back and do the next time step, etc. So that every 5 time step I write that temperature profile into a file named as explicit 1, explicit 1, explicit 2, etc. Okay, now this is a method of writing the files like that. So I can use this function which you have not seen before maybe. This is called sprintf. Okay. So I have a character string here, and into this character string I am putting a name for a file. Okay, the name of the file is explicit and what a number here, and the number is given by IB. Okay, the number is %d is given to put the number here. Okay, so now this character string will get this name explicit and whatever the number which IB takes. Okay, so IB takes t by 5. So when t is 5 it's 1, and when t is 10 it's 2, etc. Okay, now this function can be used to automatically generate file names. Okay, now this generates file names explicit 1, explicit 2, explicit 3, etc. as we run this program. So every 5 time step it will store the temperature into a file whose name is generated as explicit 1, explicit 2, etc. Okay, so now it's storing the temperature and the L value or I value in this case, which corresponds to discrete points along the rod. So we run this program, and so we compile that and we run this program, and then now we have all these data files which are written as explicit 1, 2, 3, 4, 5, etc. So this corresponds to temperature at time 5, 10, 15 up to 50. So 0 to 50 is what we have. Okay, so now we plot this one of the things. That means we get a time t equal to 5. Okay, so that's it. Okay, so temperature goes from 100 to 0 as we go from 0 to 5 in space. Okay. So what we see is that the temperature drops. Okay, and so that's what we expect. Okay, and it goes to 0 in a continuous fashion. Remember, we are only 5 points in the interior, and now we could plot this the time 2 also. So we write the next time step, that is explicit 2 or explicit 4 maybe. Okay, now that's the after a few more time steps. So you can see that by the 4, that is 20 time steps. Okay, we have actually reached the value, the steady state value. Okay, where this linearly drops. Okay, that's what the steady state solution would be, that the temperature drops linearly from one end to the other end, and that's what we see at the time at 20 time steps. Okay, so this method definitely works for lambda equal to 0.5 and gives us the evolution of the temperature profile as a function of time. Okay. So now let's look at the same program. Let's look at the same program when we change the lambda to 0.7 something. Okay, so we increase to, let's say we change this to 0.71. Okay. That's what I've written in the comment here. Then we will see that it doesn't actually work very well for lambda equal to 0.71. So what we have done is either we change the lambda, we increase the lambda, that is we either increase delta t or we decrease delta x. To increase our spatial resolution, probably we increase delta x or decrease delta x, and that's increasing lambda. Okay, and then we'll try to run this again. So let's see what we get. So we run this program, and then we again plot this as a function for the first time step. Okay, so and that's what we see. So then we see that and we increase lambda instead of getting a smooth profile as we obtain for smaller lambda. Now we have oscillations in the temperature. Okay, and we are not supposed to be getting these oscillations. We know that if I keep a rod at one end at 100 degrees and other end at 0, okay, I expect the temperature to drop in a monotonic fashion, not oscillatory in space. Okay, and actually these oscillations would blow up, and we would get by next time step we would see that we can actually get the solution correctly. So you can see that the temperature now has gone completely crazy. That is, now we have temperature going to minus 2000, plus 6000, etc. So which is obviously wrong. So this particular method doesn't work for lambda larger than 0.5. I just use a larger which is higher, okay, to get probably a better spatial resolution, and we see that the method doesn't actually work. Okay, so this is an example to show that even though very simple, this method is not very efficient in solving equations of this form. Okay, so we go back to the next our description and look at a little better method called an implicit method. Okay, so as I said earlier, the difference is that in this method, the spatial derivative in a simple implicit method, the spatial derivative, okay, on the right hand side of this equation which we have here, okay, this spatial derivative is now evaluated at time t plus 1. So that's we will evaluate all these derivatives at time t plus 1. Okay, so this derivative would be evaluated at time t plus 1. So that means that when you write this equation, okay, so that is the discrete form of the heat equation, you have all these derivatives are taken at time t plus 1. Okay. So now obviously this will not work anymore. So we have to write a different equation for that, right? So when this is all evaluated at time t, we have a very simple equation for the temperature at time t plus 1. Okay, but now we have the right hand side evaluated at time t plus 1, and because of that, now we have to, when we write this equation for time, when you write this equation separating t plus 1 and t time variables, so you will have u l minus 1 t plus 1 and plus 1 plus 2 lambda. Sorry, let me write that. Minus lambda. So we have lambda is, remember, k delta t by delta x square. So we have minus lambda ul minus 1 t plus 1, and then you would have 1 plus 2 lambda ul t plus 1 and minus lambda ul plus 1 at t plus 1 is equal to ul at t. So now we have the equation in this form, okay, and we have to solve for at the very time at t plus 1. Okay. So, now we write this equation for every spatial point L, right, and then we will get a set of linear equations. Right. So, if you write this equation for every spatial point, we get a set of linear equation, and that set and then has to be solved using matrix methods to get the correct answer. So, again if you write this for example L equal to 0, we do not need. So, we have again u0 let us say is 100, and we say u some n is equal to 0, and that is fixed at all time. Okay, for any t this is fixed. Okay. And then we write this equation starting from L equal to 1 to n minus 1. Right. So, for L equal to 1 is a special case because then this is 0. So, then for L equal to 1 we have it as 1 plus 2 lambda u1 at t plus 1 minus lambda u2 at time t plus 1 is equal to u0 at time t plus lambda times u1 at time t and u0 at time t. So, that is for L equal to 1. For all other L, that is L greater than 1 and less than n minus n less than n minus 1, we have this equation, that is minus lambda u L minus 1 t plus 1 plus 1 plus 2 lambda u L at t plus 1 minus lambda u L plus 1 at t plus 1 equal to u L at t. So, that works for all L between 1 and n minus 1. So, for L equal to n minus 1, again we have problem on this end. So, we can write that now as minus lambda u n minus 2 at time t plus 1 plus 1 plus 2 lambda times u n minus 1 at time t plus 1 is equal to u L u n minus 1 at time t plus lambda times u n at time t. Okay. So, lambda times lambda u0 and lambda u n are fixed by this, right. So, these two equations are slightly different from the other point equations. So, that will be, this will give us a set of so we have a set of linear equations, and the variables are, the unknowns are like u L minus 1, u L and u L plus 1. So, you have a tri-diagonal matrix to solve. So, we can write this in a matrix form and you get a tri-diagonal matrix, okay, with elements which will be of this form. So, I write that here. So, you will have an equation of this form 1 plus 2 lambda minus lambda, and then you have 0 0 0 etc. So, let us write for 5 points. Okay. So, you have 1 plus 2 lambda minus lambda 0 0 0 . And the next one would be minus lambda 1 plus 2 lambda minus lambda 0 0, and then you will have 0 minus lambda 1 plus 2 lambda minus lambda 0 and etc. Okay. So, you will have until you have the last point would be okay, I will write all of it. So, 0 0 minus lambda 1 plus 2 lambda minus lambda, and then 0 0 0 minus lambda 1 plus 2 lambda. So, that is our matrix, and this multiplied by, so this matrix will be multiplied by we will have then u1, u2, u3, u4 and u5. So, that is what we will have to get. Okay. So, we have to get these two, this matrix multiplied by this column vector, and the right hand side of that will be given by, this is at t plus 1. So, this is all at t plus 1. which are our unknowns. So, u's at time t plus 1 is our unknowns, and the right hand side of this equation would then be this. We think that is the first one would be u1 at time t lambda u0, and the rest would be u2, u3, u4 at time t, and the last one would be u4 at time t plus lambda u5. That will be the right hand side of this matrix. So, this is the matrix which we have to solve. Okay, so we solve this. So, we have the equation in this form, that is with the first one as with the right hand side as so our matrix equation now is u1 at time t plus u0 at time t plus lambda u0 at time t, u1 at time t, and then u2 at time t, u3 at time t, u4 at time t, and u5 is u4 at time t, u plus lambda times u, actually u5 at time t and u6 at time t. Okay, so now this point is solved by this and this are fixed, these two values, and the other we will solve for and this all values at time t. So, we know all this the right hand side, so we can solve for this equations at time t plus 1. So, that's a method, and we will see an implementation of this method in this particular program. Okay, so here is another program which does that, and we can call it implicit method. So, it's simple implicit method. So, here I am using lambda which is large, which is 0.7, okay, just to show you that it works for this large lambda. Okay, and other things are same. Access temperature is two boundaries are fixed at S0 and Sn are the two boundary temperatures, that is 100 and 0. Okay, and all temperature at time t equal to 0, everywhere else is 0. So, now I have to construct this matrix. So, here is a matrix which is constructed, right. So, I have first to start with all matrix elements are put equal to 0, right, and then I give the matrix elements these values as lambda 1 plus 2 lambda and minus lambda along the diagonal. That is along the diagonal, this is a tri-diagonal. So, along the diagonal I have 1 plus 2 lambda, minus lambda, 1 plus 2 lambda, and lambda, minus lambda as the matrix elements, and that is what has been given here. For each of those columns, okay, I have I minus 1 I, as I minus 1 I and I plus 1 as minus lambda, 1 plus 2 lambda and minus lambda. And the right hand side of the matrix which is given of this equation is given by di Si, that S, remember, is the temperature at S time t, okay, and d in this particular case S is the temperature at time t. Okay, so, here given that, okay, and there are two special cases. So, the first row, okay, the first row I have to, this is for the interior points, and the first row I have only two elements, that is 0 0 is 1 plus 2 lambda and 0 1 is minus lambda, and the right hand side is S0 lambda plus S of 0, so that is one more. Okay, this is actually the first for the first row, and for the last row again we have only 2 points, that is n minus 1 I minus 1 and n minus 1 I. Okay, now this is the last point, that is actually I is n here. So, n minus 1 n minus 1 and n minus 1, yeah, n minus 1 and n minus 1 n. Okay, so sorry, I is n minus 1, so n minus 1 n minus 2 n minus 1 n minus 1. So, these are the two last points, okay, the last row. Okay. So, I am just writing these two elements and these two rows especially. Okay, so that is here I have n minus 2 and n minus 1, and here I have 1 and 2. Okay, so it's written a special case, and similarly this right hand side equation, this is u5 plus lambda u6, which I call un in the program, and this is u1 plus lambda u0. Okay, so that's the equation. Okay, so then I call this function here which finds the inverse of this matrix D. So, n is the dimension of that matrix. So, then what my idea is that I would just find the inverse of this matrix, right, and multiply with this, okay, then I will get that temperature at time t plus 1. Okay, so the advantage of that is, see, this is a constant matrix, this does not depend on the time. Okay, the matrix here does not depend on the time. Okay, so what depends on time is only these two column vectors. Okay, so once I have constructed this matrix, okay, for the given discretization I have, okay, and found the inverse of this matrix, okay, and then I can just go through a loop to find the t plus 1 as a function of t, okay, and that is what I will be doing in this part program. To find the inverse of the matrix, we know we have this a function here which finds the inverse of this matrix, okay, and so we look at that function. So is a function to which that matrix D has passed as an array of pointers, okay, which you have learned earlier, and the method this matrix the function uses is to do the LU decomposition, okay, and so we find the inverse by using the LU decomposition, which again we have found earlier. Okay, so we have the LU decomposed form of this matrix D, okay, which we had seen earlier, okay, in our earlier lectures, and then use that LU decomposed form of this matrix and supply the right hand side as 1 0 0 0 0 1 0 0 etc. We give the D matrix, the D column vector in this form, and find the inverse. We have gone through this earlier. So we have the inverse here. Okay, now this inverse is returned back into this program. Okay, so when I call this inverse function here, okay, in this program, I call the inverse function, and I pass the matrix D, and when it comes back, the D is replaced by its inverse. Okay, so because we don't need the D matrix, what we need is the D inverse. Okay, and then I do it for 10 time steps here. Okay, so I am doing it for time equal to 1 to 10. Okay, and each time step, what I do is I multiply that matrix. So this is a matrix multiplication. I multiply now the temperature at time t plus 1 is temperature at time t plus the matrix multiplied by the D, right? And then I replace D by that particular time t plus 1, and again treat the two endpoints separately, and goes back into this loop again. Okay, so the method is this: I find the inverse of this matrix, okay, and multiply this vector column vector here by the inverse of this matrix, and I find at time t plus 1 what the values are. Then I transfer the time t plus 1 values into time t into this vector, and again multiply it by the inverse of the matrix to get the next time step. Okay, so that's what we're doing here. So to start with, you have the temperature 0 everywhere except at the two endpoints. Okay, and then I multiply the matrix, the right hand side, the D column vector, by the inverse of the matrix D. Okay, this is now replaced by its inverse, right? And then I transfer what I get is into the D column vector, and I treat the two endpoints specially because they are not SM, but they are not U at time t plus 1, but they are S0 times lambda plus the U at the values. Okay, and similarly the last point, and then I write those temperature as a function of time into different files here. Okay, again I use the same technique to generate different file names, and then I store them all into different file names called implicit 1, implicit 2, etc. for every time step. And remember, I am going to run this for lambda equal to 0.7. So we will now run the implicit program. Okay, so instead of explicit, we will run it now implicit program. Okay, so that is so now we will plot the implicit method. So okay, and you see that there are no oscillations. Okay, so the temperature is, this is at time 1 and this is at time 4, etc. So there is no oscillations here, and it slowly keeps improving. Okay, so it keeps the temperature at any point in between the two ends is increasing as a function of time, and it goes towards a straight line. So what I wanted to show you here is that again I used only 5 points. Okay, so I used 5 points between the two limits. Okay, and I used the lambda which is larger than 0.5, that's I used lambda 0.7 for which our explicit method did not work, and you saw that the implicit method works for this particular value of lambda. So what is the difference? In the implicit method we wrote the right hand side, evaluated the right hand side, that is a spatial derivative at time t plus 1, and while in the explicit method the right hand side was purely a function of the temperature at time t. So that's a difference between the implicit and the explicit method. Okay, there are better schemes than this. Okay, so if you look at this particular method is again an Euler scheme itself, but only thing is that we have evaluated the right hand side at time t plus 1. Okay, so we could do even better than this by actually taking a mixture of the time derivatives at time t and time t plus 1. So that's also, that will be what we will be looking at next. So to summarize here, so we had evaluated the derivatives at time t plus 1, okay, and then we wrote down the equations for all the interior points, okay, and the two boundary points were specified as boundary conditions for all time, okay, and then we write down the equations, and we write down the equations for all interior points, okay, and then solve them using matrix methods. Okay, so we find the inverse of this matrix and multiply the right hand column vector by the inverse of that matrix to find the temperature at time t plus 1. So the other method in which we can use other implicit methods, which uses a mixture of these two derivatives, that is we could use the derivative on the right hand side, the second derivative, that is a del square u by del x square, evaluated at both time t and t plus 1 and take the mean of that. Okay, so this is called the Crank-Nicholson scheme. Okay, so in this method is again an implicit method in the sense that the right hand side of the equation of the del u by del t equal to k del square u by del x square is still a function of temperature at t plus 1 at time t plus 1, okay, but now it is a mixture of the time t and t plus 1. Okay, so again we could use the same scheme. So then we would write the equation now in this form, that is u L at t plus 1 minus u L at t by delta t. So this is our del u by del t. Right now the del square u by del t square is written as mean of the second derivative evaluated at time t and at time t plus 1. And then we collect all the terms here, okay, and write the equation now for the interior points as this one. Okay, so we have at the interior point equations as t plus 1 u minus lambda u L minus 1 t plus 1 2 times 1 plus lambda u L t plus 1 minus lambda u L plus 1 t plus 1, and the right hand side now is a function of L minus a temperature at L minus 1, L and L plus 1. Okay, so this is actually L plus 1. So there is that's the difference. Okay, so we have, instead of simply writing it as so what we wrote in the simple implicit scheme was that u L at time t plus 1 minus u L at time t divided by delta t. We wrote that as k times u L plus 1 t plus 1 minus 2 u L at t plus 1 plus u L minus 1 at time t plus 1 divided by delta x squared. So now instead of that, now you write u L at time t plus 1 minus u L at time t as equal to lambda, which is delta k delta t by delta x square, into u L plus 1 time t plus 1 minus 2 u L at time t plus 1 plus u L minus 1 at time t plus 1 plus, right, now u L plus 1 at time t plus u L plus 1 at time t plus minus 2 u L at time t plus u L minus 1 at time t, okay, then divided by half the mean. Okay. So we collect terms here and write this as now. So we have all the terms at t plus 1 onto the left hand side and all the term at the t on the right hand side. So you have ul plus 1 at time t, ul minus 1 at time t plus 1 into, so we have as minus lambda by 2, okay. And then you have ul, so we have 1 plus lambda into 2, 1 plus lambda at ul at time t plus 1, okay, coming 1 plus lambda. So there is one term coming from here and one term here, and then minus lambda by 2 ul plus 1 at time t plus 1 on the left hand side, and the right hand side then we have equation as lambda by 2 into ul minus 1 at time t plus ul plus 1 at time t minus 2 ul at time t, and then we have that's plus ul at time t. So that is our equation now to solve. Okay, so again this is in the matrix form. So we have all the time t plus 1 on the equation on the left hand side, or the t on the right hand side. So only thing it is exactly the same as simple implicit method, except that the right hand side now has to be evaluated using the temperature at L minus 1, L plus 1 and L, okay, at time t. Okay, that is only difference, and then you could use exactly the same inversion scheme. So once you have set up all the metrics, okay, again you could invert that matrix, okay, and then for every time you could multiply the right hand side by that matrix and get the temperature at time t plus 1. So that is all for when it is one spatial variable, and we will look at in the next class what happens if you have two spatial variables, that is x and y, okay, and how do we deal with implicit and explicit methods in that particular case. Okay, that is what we will be looking at in the next class.